Hello friends, welcome to my channel Selected Topics in Physics. Today I will discuss about capacitance and negative capacitance, how to model the negative capacitance and to understand when we will call this is as a negative capacitance. So first we will understand what is capacitance. So capacitance, it is the ability to store the electrical charge. Depends upon the ability to store the electrical charge. We can say this is the capacitance of this capacitor value is higher or lower. So it is defined as C equal to the ratio of delta Q and delta V, where delta Q is the change in store of electrical charge when we will change the electrical voltage delta V. So here delta V equal to V2 minus V1, whereas delta Q is Q2 minus Q1. Capacitance, this unit is farad and its impedance is defined as 1 by j omega c, where j equal to root over of minus 1, omega is the angular frequency, c is the value of the capacitance. So if we measure inductance and to represent it graphically, we can represent it is like that. This is the imaginary axis, this is the real axis, and this is the total impedance J. So this is the X, and this is the real part R. So total impedance equal Z equal to R plus J into X, and the value of impedance is omega L, that we can represent mathematically equivalent to minus 1 by omega C. So this is when we will measure the for a device as a inductor value. Next, for a capacitance, so we can also represent using inductor like 1 by omega c equal to minus omega L. So here in capacitance case, so axes are same, but the value of imaginary part is negative, and others all our variables are same. Omega is also same, the angular frequency, c is the capacitance, and L is the inductor value. So a capacitance or a inductor, which one is the real measurement, that how we'll understand, that is the most important thing in this video. So let's understand this negative capacitance using this model. So for a RL circuit, for example, there is one resistance and one inductor. We can write total impedance Z equal to R plus J omega L. That we can also write, if we write as a equivalently, there is only one capacitance value, then the total impedance value is 1 by j omega c. This is this part. So if you calculate the capacitance value from the above equation, it will come 1 divided by j omega r minus omega square L. So if we apply condition, that is the omega very greater than r by L, that is for a higher frequency. So we can also write omega L very greater than r, or omega square L equal to or very greater than omega r. So both sides we have multiplied using omega. So then if we replace this omega square L, or if we put this condition in this equation that omega square L much greater than omega r, then the capacitance will come equal to minus 1 by omega square L. So here the important thing is that we have modeled this RL circuit equivalent to a capacitance. Then we extracted the value of capacitance, and we have found it's a dependence with frequency that 1 by omega square, and that is happened when we have considered the frequency very greater than R by L. So for a genuine inductive behavior, the capacitance or observed negative capacitance, that should happen at higher frequency, that is omega much greater than R by L, and its frequency dependence should be as 1 by omega square. So if two conditions are satisfied, then we will say the observed or measured negative capacitance is an inductive behavior. Otherwise, it is a negative capacitance. So this is the reference I have used. So there are many applications of negative capacitance. So it is not like that it will show always a negative capacitance or a inductor. So, so there are much more research articles in this topic. So if you want to understand more, you can write in comments or you can follow this reference. Thank you for watching.